the course Advanced Reaction Engineering. So, we are going to discuss about solid catalyzed reactions, the reactions and diffusions. So, here particularly we will discuss when we consider a gas as a reactant, let us say, and solid particles or solid catalyst is there. So, when there is a reactions, so with that diffusion is also there. So, that particularly we will discuss. So, in heterogeneous catalytic systems, so the reactants may be in the form of liquid or gas and the catalyst in the solid forms. So, and the catalyst consists of a number of pores, small pores, that may be micropores, mesopores, macropores. So, that are present in the surface of the catalyst or inside of the catalyst, so those are called pores. So, in when the reactions will take place, so the reactant molecules may come interact with the surface of the catalyst or active sites of the catalyst, but in the outer surface of the catalyst or active sites are present, that is easily means accessible by the reactants, and then reactions will take place. But when we talk about inside of that catalyst, there are so many small spores are there, small active sites are there. So, those are not accessible as it is accessible outside of the catalyst surface. So, therefore, so internal surface concentrations, rate of reactions, that would be different from the external surface reaction, since catalyst is the solid surface and through that pores reactant molecules we have to pass through that. So, if all reactants molecules are not accessible, means active sites are not accessible by the reactants. So, then rate of course point to point inside of the catalyst, outside of the catalyst, that would be vary. So, here you can see one spherical particles or spherical surface, you can say this is the catalyst spherical surface we have considered. So, inside of the catalyst I said there are so many pores are available. So, these are called spores, micropores, mesopores. So, these are depending upon dimensions of the pore size, we can classify that. So, but that we will discuss later. So, means so many pores are there. So, when reactant molecules comes, they interact with the surface, active sites are present. So, these are the active sites, let us say, but so whence the active sites are present inside of that pores. So, reactant molecules we have to diffuse through that pores to the internal surface, and then they reach to the active sites, and then their reactions possibility is there. So, if you talk about the reactant concentration, see here reactant is the A. So, reactant concentrations, this is the surface concentrations of catalyst surface, and whence the reactants we are considering means initially that is feeding inside of the reactor, that having higher concentrations or close to CAS concentrations. So, this is called bulk concentrations from the means when it is feeding and reaching to the catalyst surface. Let us say here catalyst is there. So, reactant molecule is passing through this way and it is interacted this way. Okay. So, here this is bulk concentration CAB we can say, and this is CAS, that is the surface of the catalyst particles, the reactant molecule reach, that concentration is the surface concentration. And so once it is diffused inside of the pores, so here this is Ca concentrations at different locations, we can say Ca1, Ca2 like that, Cas. So, here the concentrations means surface to inside of the pores, the concentrations are not the same. So, that is means molecules usually diffusion is there, and through diffusions molecules will diffuse through this catalyst particle. So, this part actually means whenever we are considering reactions, with that diffusions also we have to consider. So, this diffusion strongly depends on the catalyst particle size. If you take larger particle size, means whenever the reactors we have chosen, so there the catalyst particles this size we can consider, or we can consider this size. Okay. So, or we can consider very small particles. So, depending upon the our selections of the particles, so same catalyst, but we are giving a particular shape of the catalyst whenever we are formulating the catalyst, and after that we are giving the shapes of the catalyst. The dimensions, if it is spherical, may be different category, we can make it. So, depending upon that, the diffusions means reactions would be everywhere, but the diffusion also be present in the catalyst when it is we are treating for the reactions. So, let us say A is going to, so for this particular system's catalyst, if we consider a spherical catalyst particle, with that diffusion and reactions that we will consider, and we will design some equations. So, ordinary differential equations or secondary differential equations will derive, and then so using some boundary conditions we will solve that boundary equations, and to get a equations that equations easily we can solve if we know the particle dimensions or other parameters. So, easily we can say or predict that what would be the concentrations at different locations inside of the pore. So, and how that would be affect means overall means rate of the reactions or effectiveness. So, that the things we will discuss. So, here let us say A is going to be, that is the reactions, and that we are considering in a spherical catalyst particles. So, here the pores are available as said. So, the pores if we talk about the pores are not straight like this. So, here dimensions are not the same. So, pores may be different dimensions it may be. So, it may be here larger diameters, after that pore diameters decrease, and then narrowing or more diameter gradually decrease. So, in different locations if we consider this the catalyst particle surface or at this particular points here are different. So, along the means cross sections at different locations inside of the pores are not the same, since the catalyst particles is sphericals and pores that we have not control. So, if and that is different means diameters or different surface area may be there. So, here A1, so here may be A2 or here may be A3, the surface area or cross sections area inside of the pores we can say like that. So, okay. So, varying cross sectional areas may be there, and through that diffusions will take place. So, before that considering means how diffusions and diffusions is there. So, diffusions here the diffusions spherical particles we have considered. So, here the diffusions or reactions means this is the let us say r diameter is the radius is r is the radius capital R. So, from this is the center, this is the outer surface. So, here we will do some means flux or radial flux means variations of the concentrations from radial directions that we will consider. Here we are considering a flux, radial flux, that is the WAR, that is the flux we are considering. Here dE, that is the effective diffusivity through that pores, or it is called Knudsen diffusivity. These are the terminology that I am discussing, and then details we will discuss. So, means whenever molecules is diffusing means from the fixed law of diffusions or equimolar counter diffusions. So, there the diffusions is called bulk diffusions or molecular diffusions, and here when it is inside of the pores, molecule is passing from one point to the another point due to the concentration gradient or concentration difference inside of the pores. So, that is usually called Knudsen diffusivity, and it is expressed in terms of d small e, and bulk diffusivity or equimolar counter diffusions you can express dAB or dA, whatever, this way we can express. So, that is bulk diffusivity, and this is Knudsen diffusivity we can say. So, now Knudsen diffusivity and bulk diffusivity is related with that using this equation. So, these equations we have to use, means once we know the bulk diffusions and other parameters, then Knudsen diffusivity or dE we can easily find out using this. So, here d is the bulk diffusivity, and here phi p, that is the porosity, means in that catalyst so many pores are there. So, inside of the pores, so porosity factors, that is the phi p, that if you know that we can put it here for that particular experimentally you have to measure that, and sigma c and tau, that also we have to find out. So, what is sigma c, that is the constriction factors, and what is tau, that is the tortuosity factors it is called. So, actual distance travelled by molecules between two different points and to those points shortest distance. So, ratio of let us say molecules is moving this way. So, this is the shortest distance, and this is the actual distance molecule is travelling from here to here. So, this is the actual distance is this, and this is the shortest distance between the that ratio of two distance is called tortuosity, and phi is the I said porosity, void volume by the total volume, and sigma c is the constriction factor. So, it actually reflect the variation in the cross sections area that is normal to the diffusion. So, when sigma c is actually it is the minimum to the maximum to the minimum pore areas. Okay. So, it is actually ratio of pore area. So, here I said inside of that pore, so at different locations, here pore area is let us say this A 1, this is A 2, here it is A 3. So, pore area are different at different locations. So, constriction factors actually the ratio of maximum to the minimum pore areas, or you can say sigma c, that is the constriction factors as a functions of beta, beta equals to area A 2 by A 1. So, A 2 by A 1. So, here you can see the inside of the pores, here area is A 1 and at this particular locations area is A 2. So, different locations inside of the pores, pore area may be different, and it is particularly beta is the ratio of two different area and constriction factor is the function of that beta. Okay. So, basically if beta equals to 1, the constriction factor is unity. If let us say beta equals to 10, means area ratio is very high, then constriction factor is approximately this. So, this way it is means theoretical approximations or study has been done, and based on that it is reported or we are studying. Okay. So, here pore tortuosity is, this is the shortest distance and this is the actual distance molecule is travelling. So, okay, that way it is defined. So, now effective diffusivity, bulk diffusivity, that we know. So, what is called that, and now we have to derive some differential equations to know the concentrations of the reactants. It is diffusing inside of the catalyst pellets through the pores mouth to the interior sides of the or inside of the pores for the reactions. So, diffusion and reactions we will consider. Okay. So, let us say spherical particles having radius capital R, and here Ca is the surface concentration of the reactants, and here this particular cell we are considering. So, spherical cells, here catalyst is spherical. So, inside of that sphere from center to R distance and center to R plus delta distance. So, small thickness delta thickness of the cell we are considering, within that we will do the material balance of that in terms of concentration. So, that we will consider, and after that for whole systems we will define, so or we will express the general equations. By that way we can consider. So, CH to centers means the molecules is moving from surface CH concentration to the inside of the pores, so how the concentrations will changes, okay, along the radial directions. So, now mole balance of A, since reactions A is going to B and CAS is the surface concentration and inside of that concentration is Ca. So, here we will do a develop a correlations in between that with radial direction. So, r equals to 0 to 0 or r equals to r to r any distance. So, okay. So, that way we will develop. So, at mole balance of E at steady state inside of the catalyst pellets. So, the rate at R, that equals to if flux W A R and area if we know particular points, this is the flux, W A R is the flux, a rate of mole, that is transfer per unit time per unit area. If you multiply it with the area, then rate of transfer of mass or component A, that we can know, and rate of A out at R plus delta R, that is the flux at that particular point into area, if we multiply that. So, then it would be equation 3. So, flux at two different rate of A in at R and rate of A out at R plus delta R, that we know, okay, using equation 2 and 3. So, now rate of generations of A in delta R thickness, means when A is reached there reactions will take place, and with the help of reactions means concentration of the reactions or due to the reactions the concentration of the reactants will changes. So, therefore, rate of reactions per rate we have to know rate, that would be per unit mass basis. So, R A prime, that is the rate moles per unit time per unit mass of the catalyst, mass of the catalyst per unit volumes we have to multiply, and then volume of the cells or crystallization area within that we are considering. So, rate of generations of A, that is. So, then R A prime into rho c and 4 pi r square r m delta r. R m is the mean radius between r and r plus delta r. Okay. used for approximations. Okay. So, now if we do the mole balance within that thickness over the mole balance over the cell thickness r in at A minus this is at R, this is in, this is out, this is generations, this is the material balance or mole balance over the cell thickness delta R or within R. So, this is in, this is out, this is generations. So, from this if we simplify by dividing this and taking limit delta tends to 0. So, this differential equations we can get after simplifications or doing the material balance. And if we consider the equimolar counter diffusions, means here the flux W A R that we said. So, that is at R locations we are considering. So, if we consider that diffusions is equimolar counter diffusions, the molar concentrations at constant molar concentrations. So, here flux we can define by this way W A R equals to minus d E, here effective diffusivity you have to consider d C A by d R. So, if you substitute this flux here and then if you differentiate it, and here C A is the number of moles per unit volumes in the pores. Okay. So, now after substitution of this flux here in the differential equations, and if we simplify this, then equations after substitutions it would be like this. Okay. Means this is the flux, this components that we are substituting here, W A R that we are substituting in terms of minus d d C A by d R. Okay. So, now here R A prime is the rate per unit mass basis that I said. So, when gas solid reactions is there, rate usually expressed in terms of per unit mass basis. So, here it is rate mole of A reactings per unit catalyst per unit times. Okay. So, and here the rate also different way you can express minus R A equals to per unit volume basis rate per unit surface area, that way you can express, and surface area of the catalyst usually express meter square, the unit is meter square per gram catalyst. Okay. So, here R A prime, so we can write in terms of this. So, R A prime equals to mole per gram of catalyst if we multiply surface area with this R A prime double prime multiplied with surface area. So, then we will get R A single prime. If we multiply minus R A double prime this rate with surface area, then we will rate per unit mass basis. Okay. So, here this is we can write this, and so here minus R A prime equals to R A double prime into S A. So, rate per unit area basis usually expressed minus R A double prime equals to K double prime for nth order reactions, and C A n that is the concentrations of A power n. Okay. So, this rate we are substituting here, and then this rate we are substituting here. Okay. So, then equations 8 we can write this way. Okay. Here this component we are substituted, this component we have substituted. Okay. So, then this component we have substituted. So, then you can see minus R A prime equals to S A into K n double prime C A to the power n. So, this basically R A prime we are substituting, rest are remain the same, means so, now equation 10 is there. So, now if difference equation 10 dividing both side by minus R square d E. So, equation 10 should becomes like this. Okay. Second order differential equations where K n equals to K n double prime S A rho C. S A is the surface area, rho C is the density of the catalyst, K n double prime is the constant, rate constant for this. Okay. Nth order reactions. So, we are expressing in this equation, this is the second order differential equations, changes of concentrations with radial directions or R. So, to solve these equations we need some boundary conditions. So, if we consider a spherical particles, so here this is small r, if we r equals to this is 0, r equals to 0, here r equals to capital R. So, here surface concentration CAS, and here concentrations may be different CA, here CA equals to CS, here CA equals to that difference, okay, locations means some finite value it would be there. So, boundary conditions at r equals to 0, that is the center, C is finite, means some value would be there. So, when r equals to r, concentration of A would be surface concentrations, okay. When r equals to r, concentration would be surface concentration, and when r equals to 0 means at the center of that particles. So, concentrations may be any value, that may be 10 to any concentrations value would be there, finite value. These are the boundary conditions. With these boundary conditions, these equations we have to solve to get a concentrations profiles, okay, means along the pores how the concentration is changing. So, now these two equations we have to, means this equation C11 and these are the boundary conditions we have to express in terms of dimensionless, and then we will solve that, okay. So, how to make it dimensionless forms? So, this is phi, that is Ca by Cs dimensionless concentrations, and lambda equals to r by r dimensionless radius, okay. So, boundary conditions, C is finite at r equals to 0, then psi equals to phi equals to finite at lambda equals to 0. Lambda when putting r equals to 0 means lambda equals to 0. When phi we are expressing Ca by Cas, that is finite, okay, psi equals to finite when r equals to 0. When r equals to r, lambda equals to 1, and then phi equals to Ca by Cas, that is equals to 1. So, these are the boundary conditions expressing in terms of lambda, okay. Phi equals to finite at lambda equals to 0, and phi has some value 1 at lambda equals to 1, okay. So, these are the boundary conditions. So, these are the two we have to use, and so now the molar flux in terms of dimensionless we have to express. WAR is the molar flux, in term here minus d dCA by dr. So, dCA by dr we have to first changing into dimensionless forms, we are writing this way, and then we are writing this way, okay. So, here just multiplying divisions of different components. So, we are expressing this, and now psi equals to this and lambda equals to this. So, then dCA by d psi we can express if you differentiate this, then dCA by d psi equals to Cas, and if you differentiate this d lambda by dr equals to 1 by r. So, now these two components if you substitute here, so we can get dCA by dr equals to d psi by d lambda into Cas by r, okay. So, now this we can substitute in flux equations, okay. So, once we substitute, then flux we can express this way, WAR equals to minus dE Cs by r d psi by d lambda. So, this is the flux in terms of dimensionless forms we have expressed. So, now at steady state the overall rate of the reactions, we usually express rate means changes of the moles per unit volume per unit gram of the catalyst. Here we express in terms of the molar changes or moles. Overall rate we express in terms of overall rate of the reactions equal to total molar flow depth into the catalyst pellet. So, overall rate of the reactions Ma, capital Ma, that is the molar flux. If you know flux, if you multiply it with cross sections area, then rate of changes per unit times that we can get, okay. So, M equals to overall rate of the reactions if you multiply it flux with area, so then it would gives. So, flux dimensionless forms we have developed this, and then if we multiply it with area, so then we can get it, and then rate overall rate of the reactions Ma that we are expressing in terms of dimensionless forms, okay, at lambda equals to 1, okay. So, now we have developed this dCA by dr equals to the dimensionless forms we have developed, and this is our equations, second order differential equation. We need dCA by dr that we have developed. Now, this component is required, and so this component if we want to get, we can split up this, and then we have to substitute dCA by dr here, then we have to differentiate, then we can get it this d2 phi by d lambda square equal to Cs by r square. So, now this we can substitute here, and dCA we can substitute here. So, after substitutions and dividing both sides by Cs by r square means the equations 11 we are expressing in terms of dimensionless form. The equations we have developed second order differential equation, these equations. So, we are expressing in terms of dimensionless forms. So, means these equations we have to express in dimensionless forms, and boundary conditions we have to express in dimensionless form, then you have to solve that. So, okay. So, now this equation to 11s we can express or write this way, okay, or simplify we can do after simplification by considering this component phi n squares equals to these components if we are considering. Okay. So, k n r square c h to the power n minus 1 by d that is we are expressing phi n squares, and this phi n square is Thiele modulus. Okay. So, here's equation 12, that is the concentrations we are expressing, means second order differential equation that we have developed, that we are expressing in terms of dimensionless forms. Okay. So, now the equation 12 is useful. Okay. What is the Thiele modulus? Here Thiele modulus is the surface reactions rate to the diffusional rate. Okay. Surface reactions rate to the diffusion rate. So, okay. So, here surface reactions rate to the diffusion rate we can express, or Thiele modulus we can say surface reactions rate to the diffusion rate. So, this is actually the ratio, means whenever we are considering or talking about the diffusions inside of the porous pellet. So, then if there is diffusions, then with the reactions, then we have to consider that if reactions is there, but there is no diffusion, then what would be the rate. So, this is actually basically surface reactions when there is no diffusion, and when surface reaction is there, there is diffusion. So, then this ratio is called Thiele modulus actually. Okay. This is particularly ratio of two different rate, and it is a dimensionless parameters. Okay. So, now this value of Thiele modulus is, let us say it is very large value is coming, let us say 30 is coming. So, or it may become 0.1 is coming phi n square value. So, it is small value, this is large value. So, what actually signifies this small value or large value? This actually indicate this actually surface reactions to the diffusional reactions. If it is large value, it means surface reactions is more, diffusion less, and if it is small value, it means diffusional rate is more and surface reaction is less. So, it means Thiele modulus when it is large, internal diffusion limit the overall rate of the reactions, it indicates, and when Thiele modulus is small, then surface reactions is rate limiting. So, okay. So, it actually signifies, means what the Thiele modulus, why we are going to discuss about the Thiele modulus and what it actually signifies for the diffusion and reactions. Okay. So, when once we are able to calculate the Thiele modulus of phi value, and by seeing that value we can say that means quick estimates, we can quick estimate or interpret that whether there is a internal diffusion is limiting or surface reactions rate is limiting. So, that we can express or we can conclude that. Okay. So, now let us say we are considering a reactions A is going to B. So, here's first order reactions we will consider. So, first order reactions rate usually express minus R A double prime equals to K 1 double prime into C A. So, here's if we this is the dimensionless forms of concentrations equations we have expressed this way, and Thiele modulus we have expressed, this is for nth order reactions. So, if we consider a first order reactions, then Thiele modulus and these equations how we can express or we can see. So, let us say this is a first order reaction, then if we put n equals to 1, so then equation 12 we can write this way, equation 30. So, what are the places n are there, so we can put 1. Okay. And Thiele modulus phi n square, that also we can write. So, that phi 1, that is n equals to 1 if we put, then it would be r square root phi equals to r into square root of k 1 to d. So, here if you want to know the Thiele modulus, so radius of that particles we have to know, and q 1 that is the constants we have to know, and effective diffusivity we have to know. So, these are the components if you are able to know, then Thiele modulus for this particular catalyst particle and reactions we easily find out. Okay. So, phi usually dimensionless. So, how it is? So, it is given here. So, you can see that. Okay. So, now we have equation 13 for first order reactions. Okay. And we have boundary condition these two dimensionless forms. Okay. At this and phi equals to finite at lambda equals to 0. So, these are the two boundary conditions, and for first order reaction dimensionless concentrations say ordinary differential equations we have. So, now this equation we are expressing in terms of y equals to psi into lambda or phi into lambda. So, here if you differentiate this, so we can get d psi by d lambda equals to this, and again if you differentiate this we can get this, means we have started with this. After differentiations, first order differentiation we get, again if we differentiate with respect to the lambda, this will get. So, now this d phi by d lambda and d 2 phi by d lambda square both we have. So, now these two we are substituting here. Okay. So, then after replacing and rearranging, so the equations would be this, equation 30 we are converting into equation 40 to make it simple equations, to it would be easy for us to get a solutions. Okay. So, these equations and these are the two boundary conditions we have. Okay. So, now if we get a general solution for this type of equations, it would be y equals to a 1 cos h phi 1 lambda plus b 1 sin h phi 1 lambda. So, this is the solutions of this type of equations, second order differential equations, equation 14's solution is this. Okay. So, now we know y equals to phi into lambda. So, what are the place y is there, we are replacing in terms of phi lambda. So, then after simplifications we can get this, or we can say the equation is this. So, phi equals to a 1 by lambda cos h phi 1 lambda plus b 1 by lambda sin h phi 1 lambda. So, here's this phi 1 and lambda, the lambda is the dimensionless length I said, this is the dimensionless length, and phi is the dimensionless concentrations, psi is the dimensionless concentration, and phi is the Thiele modulus. So, this is dimensionless concentrations, Ca by Cas, lambda equals to r by r dimensionless radius, and phi is the Thiele modulus, okay, for first order reactions. Okay. So, these are the components is there in these equations. So, here's another two terms, that is the b 1 and a 1. These are the constants we have to find out by using boundary conditions. Okay. So, now these equations we have to solve using boundary conditions 1 and 2. So, once lambda equals to 0, cos phi 1 lambda equals to tends to 1, and so when 1 by phi tends to infinite, then this would be 0. So, using that, so we can get a 1, and second using second boundary conditions phi equals to 1 equals to lambda equals to 1 on that case. So, we can get a 2. So, once we solve that, means these general equations if we solve with the help of boundary conditions, so then we can get this psi equals to Cas by Ca equals to this. Okay. So, equation 14 is the, so initially we had differential equations, what are the differential equations, this 11th equation, this is in terms of concentrations. Okay. So, in terms of concentration these equations we have, and corresponding boundary conditions, two boundary conditions we have, then we are converting that into dimensionless forms, and then we are transforming into these equations into this, and then with the help of we get the solutions, and then that solutions will be get solved with the help of boundary conditions. Then we can get dimensionless concentration psi equals to Ca by Cas equals to 1 by lambda sin h phi 1 lambda by sin h phi 1. So, this is the concentrations profiles actually. So, here we know lambda value and phi 1 value. So, if we know lambda phi 1 and Cs value, Cs is the surface concentration of the reactant that we are taking at the beginning of the reactions. So, lambda value means dimensionless length, and Thiele modulus if you are able to know, and concentration, then Ca value we can find out. So, this is our objectives at different lambda, what would be at different lambda, what would be that value. Okay. So, now this we can get. Okay. So, now if we plot Ca by Cs against R at different small value of phi, medium value of phi, and large value of phi, I said phi is the Thiele modulus, it may be small value, it may be a 25 to maybe 30 large value. So, depending upon that, so we can see if we from these equations if we plot Ca dimensionless concentrations and radius if you plots. So, for small phi 1 value it is like that. So, here concentrations pore concentration is very high, when it is medium concentration is this, and when it is like this the concentrations would be very low. Okay. So, this indicate actually what would be the concentration at different locations. Okay. So, when small value of the Thiele modulus it indicates surface reactions controls, when large value of the Thiele modulus indicates surface reactions is rapid. Okay. So, today is up to this. Thank you.